Today we're going to talk about logarithms, and you got an intro to logarithms with the super fun puzzle. So on this super fun puzzle, we talked about the pattern between these things that they have, like this word power. So we're going to actually do logarithms that are structured the same way this power expression is structured, and it'll make a lot of sense connecting the two now that you've kind of figured out the pattern on your own. So for the examples, you should have been able to kind of deduce that 2 to the third power equals 8 and 3 to the fourth power equals 81. And so that's where the relationship between the three numbers. So you should have been able to fill in the blanks for the rest of them based on that relationship. And then looking at the last one I think that you might have had a little bit more trouble with because 16 doesn't have an exact power that equals 64. And so it's 3 over 2 if you really think about the structure of exponents. But for now, if you just got 1.5 by like guessing and checking, then that's great. You understood the idea that it needed to be somewhere between 1 and 2 because 16 to the first power is 16, and then 64 is smaller than 16 squared, which is, I think, 256. And so this pattern is what we're going to be using today when we're talking about logarithms. Okay, so in the lesson 2 notes, you'll notice that for the homework, I've underlined everything except for 38 to 40. Those are the graphs, which is what's on the back, and we aren't going to get to that till Monday. So know that you can do the majority of the homework with this. And so right now, let's define a logarithm. So a logarithm has a base b, where b must be positive, but it can't be 1. And y is positive, and it's defined as follows. So if y equals b to the x power, then log base b of y must equal x. And again, this is the pattern that you saw on the super fun puzzle. It's just got the word log instead of the word power. So the variables I'm using, y, x, and b, are not necessarily going like they aren't standalone. I could use symbols. You're really just looking at the relationship and how they change within each other. Okay, so the first 2 examples, and a good skill that is reinforced all the time, is being able to switch between the 2 forms whenever it best suits you for any problem. Okay, so we're going to start with just being able to switch between the 2. So for example 1, we've got an exponent, and we're writing it in log form. So what we first want to find is the base, and so the base is the thing with the power on it. So in our case for a, the base is 2. So that means we're going to write log with the base of 2, and so 2 is a subscript. It's smaller than the rest, and written down kind of at the bottom of the number that was by itself equals the exponent on the base, so equals 5. Okay, so structurally, log base 2 of 32 equals 5. Again, we can see that 2 to the 5th equals 32 if we wanted to kind of go backwards. It's okay if it's written differently. So notice that in this one, the b to the x is on the left-hand side instead of the right-hand side. You just need to be able to look for what is the base of the power, because that's going to be the base of the log. So the base of my power is 1/2, and so that goes together. And then I'm going to take log base 1/2 of 1/8 equals that 3. Okay, so I want you guys to take a minute and try C and D for yourselves. So if you could pause the video and let them work, and then check answers with them as soon as they're done. So now let's look at example 2. So for example 2, we're doing the opposite. We've got a log equation, and we're writing it as an exponential equation. I like these better because I can evaluate whether my answer is correct or not by just looking at the equation, because it should end up being a true statement. So when we look at this first problem, we have log of 0.01 equals -2. So we should notice right away that we're missing a base here. So there should be a little number down here, but there isn't. And so one important thing to know is that if we're missing a base, the base is actually a 10. Okay, so I know typically when things were missing, like it was a 1 or a 2, in this case it's a 10. Okay, so that means that we're going to add a little 10 there so that we can switch this to exponential form. Okay, so that base is going to be the number that has the power attached to it. Remember that the power in the log is the number that's over by itself. So this means 10 to the negative 2 is going to equal 0.01. And again, I said we can kind of check to make sure if it's correct by just checking this side to make sure it equals 0.01. So you could type 10 to the negative 2 power in your calculator, or you could think about it as it means 1 over 10 squared, which is 1 over 100. And if you divide 1 over 100, you should get that 0.01. Okay, so let's try another one. So we've got log base 3 of 27 equals 3. And so 3 is our base. The other 3, the one by itself, is our power. So 3 to the third power equals 27. And again, notice that I should know that. That should be a fact that I have memorized. So I know that 3 to the third power is 27. So that helps me understand that this is correct. One thing I wanted to go back to is in example 1C. You should have gotten log base 10 of 1 equals 0. And so actually you can rewrite that as just log 1 equals 0. Okay, so know that that's the simplified version of something with a base of 10. You just dropped the 10. Okay, so it's a known fact that if I just see the word log, it's a log base 10. So that's something that you should know. So I want you guys to take a second and do C and D. So if you could pause and then check answers and then press play again once everybody's finished. So example 3 is asking us to evaluate. And evaluate is actually kind of what you were doing in the Superfund puzzle. So you were finding which power of the base is equal to that value for y, or the value that was inside the logarithm there. And so that's the big idea here that you've already kind of practiced. So some of these will be very simple because you figured out the pattern and you understand it. Otherwise, they're going to be, I'm going to teach you skills that will help make it a little bit easier. Okay. So for example 3, evaluate, so meaning we want to find what power of that base is equal to, for example, in A, 100. What power of that base is equal to 5? What power of that base is equal to 1 over 32? What power of the base is equal to 27? And so what we want to first do is set everything equal to x, because we don't have something on both sides of the equation right now. And so we want to make sure that we have something we can then switch to exponential form. Okay, so as soon as you see the word evaluate, if it doesn't have an equal sign somewhere, then you need to make it equal to x. So we have a variable to solve for. Okay, so what we're going to do is now switch to exponential form. So for this first one, we're missing our base. So remember we said that means that it's a 10. Okay, so I have a log base 10 to the x power equals 100. Okay, so based on our power pattern and what we saw, we should be able to see is 100. So x must be 2. Another way that we can try to do this is to try to rewrite both sides with the same base, and then we can set our exponents equal to each other. So what I mean is I can rewrite with a base of 10. Okay, so I can rewrite 100 as 10 squared, because I know that 100 is equal to 10 squared. And then what I can do is I can now ignore my bases. So my exponents are x and 2. So I have this expression, x equals 2, if I ignore my bases. And that's essentially a strategy to get the power. So if you can't do it in your head, you'd want to kind of try to rewrite it with that base. Okay. And so we didn't necessarily have to do that method for this one, but we will for these future ones because they're going to get a little bit more complicated. Okay, so if we switch this next one into exponential form, we get 25 to the x power equals 5. And so what's going on here is 5 is smaller than 25, so I can't rewrite 5 as a power of 25 the way that I did. I was able to here. So I might have to rewrite 25, right? So I always want to kind of rewrite that bigger base as a power of the smaller base if I can, okay? So if I'm looking at this, 25 is the power of 5. I know that 25 is 5 squared, okay? So I'm going to rewrite that 25 as 5 squared. And I can think about 5 as 5 to the first power because I'm going to need to ignore my bases eventually, okay? Remember that if I'm raising a power to a power, so 5 squared raised to the x power is the same as saying that I have 5 to the 2x power equals 5 to the first power. And so now I can ignore my bases and I get 2x equals 1. Okay, so I'm setting my exponents equal to each other. 2x equals 1, which means to solve, I would divide both sides by 2. So that means that our answer here is 1/2. And if we remember 1/2, that means the square root. So what we're saying is that the square root of 25 is 5, okay, which is how that number is coming about. Okay, so if my base here is bigger than the value that I'm taking the log of, so 25 was bigger than 5, then I'm probably going to have a fraction because I'm going to need to take some kind of root to make the number smaller. So for C, we've got 2 to the x power equals 1/32. And so when we have a fraction, what we saw in the Superfund puzzle was that our answer ends up being negative. Okay, so really what we want to kind of think about is, can I write 32 as a power of 2? And yes, I can write 32 as a power of 2. 32 is 2 to the 5th power. And so if I think about that as 2 to the 5th instead, remember that when it's 1 over that, that really means that I have 2 to the x equals 2 to the negative 5, which means that I can ignore my bases and my answer is negative 5. Okay, so we saw that when the base is bigger than the value I'm taking log of, I get a fraction. When I can get a fraction. When something's a fraction and something is not, that's when I'm going to get the negatives, right? So if I would have had like a fraction in here and a whole number here, the same kind of issue would have come up. Okay, so then for the last one, this actually is going to kind of go along with our 16 and 64. And so when I rewrite this guy, I've got 9 to the x power equals 27. Okay. And so in all of these, I only had to rewrite one side as a power of something else. What's going to happen here is 9 squared is 81. So I can't write 27 as a power of 9 because it's going to be some kind of decimal or something. So what I actually want to do is try to rewrite them both as something. Okay, so I may need to rewrite both if I can't figure out that pattern right away. So I think about 9. 9 is the power of what number? 9 is the power of 3. So I can rewrite 9 as 3 squared. And remember, that's being raised to the x power. And I can also write 27 as a power of 3 because it's just 9 times 3 again. So it's 3 to the 3rd power. So what I can see here is that I really have 3 to the 2x equals 3 to the 3rd. And so if I ignore my bases, right, set my exponents equal to each other, I get 2x equals 3. So if I divide both sides by 2, that's going to give us 3 over 2 as our power. And again, if we kind of think about what this means that I'm taking 9, taking the square root of it, and I'm raising that to the third power, right? So a power of 3 over 2 means my index is 2, my exponent's 3, the square root of 9 is 3, 3 cubed is 27. Okay, so remember that fractions mean radicals. The last thing that we're going to talk about today is inverses. So if I'm looking at finding the inverse of a log function, because I can switch log and exponential functions together, they're inverses of each other. So once we start to solve problems, we're going to use logs or exponents to isolate some variables. So right now we're just looking at how can I take my equation and find the inverse of this log function. And so remember that finding the inverse, we switch x and y first. And so if I take and I switch x and y in this first equation, I get x equals log base 4 of y. Next, it's asking us to isolate the logarithm. So in this problem, the log already is by itself, right? The log base 4 of y is like one piece. So that means that we can go straight into changing it to exponential form, that it's already isolated, as opposed to like with b, see how we have the +1, we've got the 1/3 and c, and so those will take this step, whereas this one we don't have to do anything. So if we switch to exponential form, so we should be professionals at this now, 4 to the x equals y, and then it's telling us to solve for y, but hey, y is already by itself, so this one was pretty quick. We just switched x and y and then changed it to exponential form. Okay, so when I just have a log, it's a lot simpler of a process. So next for b, we've got log base 3 of 4x plus 1. If we compare this to c, notice that the 4x is the only thing in the log for b, whereas x minus 2 is all in the log for c. And so what that means is I can kind of think about it as though there were parentheses around the 4x, so that 1 isn't in the log, it's not attached. So when I switch x and y, so we've got x equals log base 3 of 4x plus 1, 4y plus 1. And then I can now isolate the logarithm. So remember that we said this is all the log, so I have to subtract 1 from both sides, which gives me x minus 1 equals log base 3 of 4y. So now all I have is the log, the base, the thing that I'm taking the log of, and so I can switch it to exponential form. So if I switch to exponential form, I'm going to rewrite this as 3 to the x minus 1 power equals 4y. So kind of think about it as the piece that was with the 3, they switch, right? So the x minus 1 ends up as the power, the 4y ends up by itself. In order to isolate y now, I'm going to have to divide both sides by 4. And the important thing about here is that we cannot actually add, subtract, multiply, or divide into our base because that variable is in the exponent. Okay, so we cannot add, subtract, multiply, or divide into the base into the because of the variable. No, just because of the exponent. Okay, so the 3 has this power, so I can't like divide 3 by 4 and write 0.75. It doesn't work that way because 3 has a power on it. The way that I would write this would be an acceptable way to write this, but typically you should write it as 1/4 times 3 to the x minus 1 equals y. I wouldn't mark you wrong if you wrote it as 3 to x minus 1 all over 4. It would still be appropriate, but this is more precise of an answer. So for our last one, we're going to follow the same process. So we're finding the inverse. We've got to switch x and y. So we're going to rewrite it as x equals 1/3 log of x minus 2. We want to get that log by itself. So right now that log is being multiplied by 1/3. So remember, to get rid of multiplying by a fraction, we want to try to multiply by its reciprocal, which in our case is 3/1. So on the left side, it's just going to turn into 3x. On the right side, the whole idea was 3 divided by 3 ends up being 1. So we just got 1 log of x minus 2. And then for step 3, we're going to change it to exponential form. So remember that if there is no base, we really have a base of 10. So we're going to rewrite this as 10 to the 3x power equals x minus 2. Uh-oh. I have 2 x's. So let's go back. We were supposed to write a y here. So hopefully you guys caught that before I did. So we had a y here, we had a y here. This guy's a y. I'm going to erase that so that it looks a little better. So hopefully you caught that before me, because we need to figure out what this is if we solve for y. So if I don't have a y, I can't solve for it. So we want to get y by itself. Currently, it's sub 2 is being subtracted from it. So we're going to need to add 2 to both sides. Remember, because this 10 has a power, I'm not going to make this 12 to the 3x. I'm not allowed to add them together. This is going to be 10 to the 3x plus 2 as my inverse function. Okay, so remember that we did a lot. And so there is kind of a lot of work for this. So you're doing on page 458, you can do 11 through 25, 50, 55 to 59, 67 to 71, all of those except for 50 are odds. Okay? So get to work.